trying to tell you something about my life.
I'm trying to tell you something about my life.
Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. Trying to tell you something about my life. I love that line because I think I sing it very well. That is Closer to Fine by the Indigo Girls. Awesome song, and we are getting closer and closer to fine as we explore complex numbers. And now we are going to talk about argument and polar form, part one. Hopefully it's only two parts. We shall see. Let's move forward, shall we? All right. Pay attention here. We know that the direction of the vector AB, yes, if I go over A and up B, it can be described by its angle from the positive real axis. Okay, so if we have the complex number A plus BI, yes, and we represent it with the vector OP, that vector OP makes an angle of theta with the positive real axis. So what we call the angle theta between vector OP and the positive real axis is called the argument of Z, or simply one of my favorite mathematical abbreviations, arg Z. Arg Z. Arg Z is just this angle right here. Our domain, to avoid confusion, is from negative pi to pi, and pi is inclusive. Clearly, real numbers have argument of 0 or pi because they're going to lie along the real axis, and purely imaginary numbers have argument of pi over 2 or negative pi over 2 because they will lie along the imaginary axis. Okay, that's easy. And before I continue, let me just say, this is a lot of things that you know already just applied to the complex plane. And a lot of folks just get very uptight over all the new symbols and abbreviations and whatnot. And it's just really, those symbols clearly are so we can manipulate the different things that we're going to come across, and also to make our life easier by not having to write out a whole bunch of things. So, we've seen the Cartesian form of a complex number. We know that's A plus BI. We can also put it in polar form. Polar is just based on an angle, that's all. And we know from our unit circle study, really, that any point P that lies on a circle with center 0, 0 has an x-coordinate of r cosine theta and a y-coordinate of r sine theta. That's just right triangle trigonometry, folks. And on the Argand plane, the complex number represented by OP is r cosine theta plus I r sine theta. Factor out an r, and so that's r cosine theta plus I sine theta. Same exact thing as on the Cartesian plane, except instead of x and y, we have real and imaginary, and the only difference is we're just throwing in an I there. That's all. That's all. And we know that r is equal to the modulus of z. That would be the radius. And so we are going to define cis theta as being equal to cosine theta plus I sine theta. So then the complex number z can be written as the modulus of z cis theta. But please remember, r is equal to mod z. They sum everything up here. Any complex number z has Cartesian form, x plus yi, or polar form, z equals mod z cis theta. Cis is cosine I sine. Cosine I sine. Say it, it's fun. Cosine I sine. Don't forget the plus. Aight? All right, now put an r here. You'll see why in a second. Z equals r cis theta. And then this just defines everything. Mod z, modulus of z. Theta is the erg of z, and then cis theta equals cosine theta plus I sine theta. Cis theta is just an easier shortcut to write this. Don't be freaked by cis theta. Why do I keep writing r? Well, because that's how it is presented in our formula booklet. Okay, so this is the same thing from the last page. And we're going to see that if z equals mod z or r cis theta, then its conjugate is equal to mod z cis of negative theta. That should make perfect sense to you. We did that before, also with your study of the unit circle. That should make perfect sense to you as well. So let's try some things. We need to write this in polar form, and I have copied and pasted from what appears on your formula sheet. So I want to focus on this, r cis theta. So let's take a look at A. Okay, so for number A, they're asking us to write 2i in polar form. Well, what does 2i look like? First of all, in Cartesian, that's really 0 plus 2i. Say yes. And this is what you should visualize in your head. Yes? So we have the real and we have the imaginary. So 0 plus 2i is just going to be 1, 2, right? It's going to be, if I drew it as a vector, ooh, that is a crooked vector, but I followed it. There you go. That's it, right? So what is the argument? Okay, what is the argument of this guy? We need to put it in this form, and theta is our argument. Well, that's the angle from the vector, between the vector and the positive real axis. Well, what is this angle? It's simply pi over 2. So z is equal to 0 plus 2i is equal to which is 2, magnitude of z, right? 0, the square root of 0 squared plus, or the modulus of z, sorry, same thing, 0 squared plus 2 squared is 2. So this becomes 2 cis pi over 2. How about them apples? Huh? How you like them apples? Right there. Same idea with b. Okay, negative 3. Well, that's negative 3 plus 0i. Yes? And I could write equals z, but I think we got it figured out. Yeah, so negative 3, if this is real, this is imaginary. We're going to go pink here. That would just be this vector right here, wouldn't it? Out to negative 3. Are you with me? So my r is 3. Clearly it's of length 3. You know, you don't even have to think of the square root of negative 3 squared plus 0 squared. So that would be, and again, this is modulus, so the distance. So it's not a negative, it's a positive. So this would be 3 cis argument. What's the arg? Arg. Boys and girls, that is pi. There you go. So that would be 3 cis pi. Okay. Easy peasy, man. Don't be freaked out by the cis. It's awesome sauce. What about 1 minus I? Okay, so let's think about this. Let's represent it with a 2D vector. Real, imaginary, right? So I'm going to have to go over 1, yes, and down 1. Yes, these are still numbers here. It's just that they're multiplied by I, right? So that's going to be right here. So my vector is going to be right there, boys and girls, isn't it? It's going to be right there. Okay. So what is, remember we need r cis theta. Well, r is mag z, which in this case would be the square root of 1 squared plus negative 1 squared. Just writing that out just so you see it, which is root 2, baby. Root 2. So 1 minus I. Oops, I should put an equal sign from here down to here. Arrow connecting it. Sorry. Okay. All right, so 1 minus I is equal to root 2. That's my r. Cis of the argument. Well, what's the argument? What's the argument? Well, if I just go down 1, right 1, down 1, I'm going halfway between the axes, aren't I? Degree-wise, that's 45 degrees, yes, if it's a positive angle, or pi over 4. But since we're going in the counterclockwise direction, we think of that as negative pi over 4. So this becomes root 2 cis of negative pi over 4. Equivalent, equivalent, equivalent. Okay. Let's just do this real quick. Let's convert this to Cartesian form. Root 3 cis 5 pi over 6. So that means we need to write it like in a plus bi or a plus ib. Yes? Well, remember that cis theta is equal to cosine I sine, cosine I sine, cosine I sine. It's so easy. So it's cosine theta plus I sine theta. This is so easy. It's so easy. So this equals root 3 times cosine of 5 pi over 6. You better know what cosine of 5 pi over 6 is. You better know. Plus I sine of 5 pi over 6. And if you know cosine, you know sine. And if you don't, I don't want to know about it. Don't tell me. If you don't know, just know. Right? All right. Okay, so this becomes root 3. Cosine of 5 pi over 6 is what, boys and girls? I know you know it's negative root 3 over 2. Plus I sine of pi over 6 would be, has to be 1/2, boys and girls. Please tell me you know that. Please, please. And we distribute through there, and we get what? Negative 3/2 plus root 3 over 2, I. There you go. Okay? Say it with me. It's so easy. We are closer to fine. Let's see how the Indigo Girls are doing. Really, really like this song. I shall see you next time, but for now, I am...